All right, I promised you a video narrating what everything's doing just to make heads or tails of the code, and to kind of, especially like with the modules that I added to allow you to test it on your board without having other boards or without having any sort of other signal source. So first of all, I'll just go over the general architecture. So one thing is everything's powered by a clock. Every single module is going to need a clock, and that's just the standard system clock. I redid the LED driver module for the example that I posted, so it doesn't do the clock divide thing at all. It just counts in sort of a normal way. So we have the data in, so the PWM data in module. Everything inside the green box is like the actual design. Everything in here is the what you really should have. And then these modules that are over here, these are just to help you simulate the behavior on the board. So inside of here, you have a stream of data coming in on pin JB, and then that stream of pulse width data gets converted to your 42 bits of data, and once that 42 bits is valid and ready, the load drops low. That should have your module spring into action, so your module needs to, the data consists of 12 bits of address followed by a red, green, and blue. It needs to do one of two things. If the address is 0, it needs to have the red, green, and blue show up on these pins to the LED driver and pulse the LED load pin low. If the address is not 0, it needs to reduce the address by 1, and then that reduced address plus the data all in that 42-bit bundle needs to show up as valid on this output to this module here, and load drops low. The PWM DAT out module, this just takes in that 42 bits. As soon as the load drops low, one by one, it starts outputting those bits. If it's a 1, it outputs a wide pulse width. If it's a 0, it outputs a short pulse width. And then the output is on JA. It's on pin JA or JA simulate. So what we've done to produce the stream of bits coming into this simulation, we've just made another version of the data out module, and we're feeding into its switches. So I think it's the first 3 switches are the last 3 bits of the address. All the other address bits are 0. Then the next 4 are the most significant 4 bits of red. All the rest are 0. The next 4 are the most significant 4 bits of green. All the rest are 0. The next 4 switches are the most significant bits of blue. All the rest are 0. And then the load is switch 15. So you have to drop switch 15 low to actually load that data in. Then this module will produce the PWM stream that then feeds into your actual design internal to the code and does what it needs to do. And on the output, we have that stream that's coming out. Instead of using pin JA or JB, you can use JA simulate, JB simulate. These basically, instead of being a physical pin to the outside of the board, what we're doing is just creating a wire instead. And so ultimately, once you test it and it works, you're going to have to get rid of the PWM DAT in, get rid of the PWM DAT out, and instead of this being JB simulate, it's just going to be JB, and you're going to have to enable that output pin JB in your constraints file. And instead of being JA simulate, this is just going to be JA. You have to enable that JA output in your constraints file, and that's the only difference. So once you know it's working, you can just make those little modifications, and it should work when it's connected to the other stuff. The LED driver gets 10 bits red, 10 bits green, 10 bits blue, so 30 bits total for the color. When load drops low, it starts doing the timing-based drive of the red, green, and blue LEDs. I didn't show it here, but it's like what? It's like LED 16B, LED 16G, LED 16R. I should have shown it. I meant to add it before I started this video, but so there should be 3 outputs to the red, green, and blue channels of that LED 16, the RGB LED. Okay, so we're going to jump into the code here now. So we'll start with we'll start with the LED driver module. So LED driver. Oops. Let me see if I can. Interesting. I can't zoom in. All right, well, sorry. Hopefully you have a high enough resolution screen you can zoom in here. So the module is 10-bit RGB, is what I call it. So it takes in clock, it takes in load. It's called N load just because it's not load. So it's, it's an active load input. in red, in green, in blue, LED red, LED green, LED blue. So these LED red, LED green, LED blue, the top module needs to connect these 3 pins to the actual output pin on the FPGA. So this needs to be connected to that, whatever, LED 16B, LED 16R, LED 16G. And in red, in green, and blue, these are 10. As you can see here, these are 10-bit inputs each. So that's the 10 bits for red, 10 bits for blue, 10 bits for green, and load. Internally, we have registers, LED red, LED green, LED blue. These are the registers used to drive the output to the actual RGB LEDs. We have a couple of registers, so we're using a couple flip-flops for the end load. This is just used for metastability, so we're just buffering that input end load through 3 flip-flops. We have the first input register which might be metastable. We have another register which will not be metastable, and then one following that which will not be metastable. So the reason we're clocking it through 3, the first one is for metastability. The next 2 are used so that we can compare the values in them to see when we have a falling edge. Clock count, we have 16-bit clock count. And then internally we have these registers that one register is for the counter and one register is for the blue, red, and green. So, okay. So I'm not sure I need, I'm not sure what, we'll see. Okay. So this is what, so end load falling is equal to end load SD and end load. So there's end load stable double. So there's end load stable double. So end load stable or whatever. So we have one stable register that feeds into a double clocked register. So this is the older data. This is the newer data. So what it's saying is if the older data is high and the newer data is low, then end load that means it's falling. So if the older value is high and the newer value, 1 clock cycle newer, is low, that's the falling edge. So this is our falling edge detection. So we say always on clock, so every clock cycle. All this does is it takes that input load and it runs it through these 3 flip-flop buffers. So again, the first one's metastable, the next 2 are stable, and we use 2 stable ones to detect the falling edge. And we say if end load falling, so end load falling, again, that should be based on this logical expression, end load falling should only be true for the 1 clock cycle when the older buffered bit is high and the newer buffered bit is low, which shows that falling edge. So when that happens, we take the inputs, the 10 bits red, 10 bits blue, 10 bits green, and we store those inputs to our registers. We store them to our internal registers in this module. So now it doesn't matter if those values change. We've stored them internally. It's done. It's okay for them to change externally. And then this is all on every clock cycle. We set clock count. We increase clock count by 1. And we say if clock count is equal to 1024, begin clock count goes to 0, LED counter. So basically, this is how I'm slowing down the clock now. So I have my master clock, which is at 100 megahertz. And then I have clock count going, counting up to 1024. So that's going to be about, so if we have 100 megahertz, 1024 counts is going to be close to, 100 kilohertz? So we're increasing LED counter at a speed of about 100 kilohertz. So this is our way of generating. LED counter is changing at 100 kilohertz, which is going to be, we're not going to see a flicker. So 100 kilohertz with about 1024-bit data is going to be, what is that going to be? About 100 hertz. So that's going to be fast enough that we shouldn't be able to see it, and it'll work out okay. So. And you could, if you do see a flicker, if you do notice a flicker, all you have to do is drop this value down. If you drop this value down to where you're only counting up to like 512, okay, well now you're slowing the clock. Instead of slowing it to about 100 kilohertz, now you're slowing it to 200 kilohertz. It's going to be twice the frequency. It's going to be less likely to see that shake. But the oscillation, the shake in LEDs normally only happens when it's at 30 or 60 hertz, just because if there's fluorescent lights, you'll tend to see that. But it should be fine at about 100 hertz. Okay, so then clock count, LED counter is just this thing that every, at a speed of at a speed of about 100 kilohertz, this LED counter gets incremented. And LED counter is going to count, oops. Yep. So LED counter is only 10 bits. So the reason we just keep counting LED counter up forever is because once it maxes out and all 10 bits are 1, it's just going to automatically go back to 0. So we don't have to like reset it when it gets to the top. All of our red, green, and blue are between 10 bits of all 0 and 10 bits of all 1, and our counter is the same. And so this is going to work. So we basically say assign LED blue equals LED counter less than blue counter. This is the technique we use. So if the value of blue, which is stored in blue counter, is like 100, then only for the first 100 out of 1,024 counts of LED counter, only for those first 100 is this LED going to be turned on. And that's how when the LED value is smaller, it's a dimmer light. When the LED value is bigger, it's a brighter light because it stays on for more of that count. If it's counting from 0 to 1,024, the full brightness is 1,024, where this expression will never be true. So LED counter will never be less than 1,024. So that's the case where this light is always on. And the worst case scenario is if the LED value is 0, this will never be, so if the LED value is, if the blue counter is 1024, this will always be true. If the blue counter is all 1, this will always be true. If blue counter is 0, this will always be false. So, actually, I guess this won't be true. It'll be one time where this turns off. Yeah, so there will be one clock cycle where this turns off. Well, we could change that to less than or equal to, I guess. No, we don't want to change it to, no, this is what we want. This is good. This is what we want. Because it's going to be off, and then, yeah, well, maybe I screwed this up a little. Oh, whatever. So basically, the blue, red, and green is going to be on for as many clock cycles as out of 1024 as is the value stored in that register. The bigger the value, the brighter the light. Okay, hopefully that makes sense. So that was the LED driver here. So let's go to PWM data in, and to look at that, let's go to this next slide. So PWM data in. So we take in one data input, one bit data input, clock input, and then the outputs are, we get the data in as a serial stream, we output it as a 42-bit array, or sorry, a 42-bit vector, and then we drop ND good low when it's correct. When it's complete, all 42 bits, we drop ND good low. So we have a register for the bit count, and that's just, it's got to count up to 42. We have a couple phases here. Those are shown on the other slide. So the biggest thing that's not shown on the other slide is phase timeout. This is where if it takes too long between bits, we consider that a timeout condition and we reset. We go back to 0. And that's good for, like, if you plug a board in midway through data transmission, you're not going to get all 42 bits. You need to have something that tells you, okay, we started halfway through our data, ignore that, and then just wait until we get the next valid thing of data. And then there's also the phase data complete. So if we did get a complete data, we go into phase data complete. So if we got all 42 bits, we go into that. If somewhere in the middle of getting data, it waited for longer than the timeout time, that counts as a timeout, and we have to go in phase timeout. Okay. Clock pulses to data. This is not correct for the spec, but it's just you can just put whatever you want. I mean, to test it, you can put whatever you want. The only thing is this value should be in the middle of whatever two values you're using here. So these are 20 and 40. This one needs to be dead in the middle of that, so it's 30 in this case. And then we say timeout is 200. So internally, we have a clock count register, which is, I think, excessively big. We have our data buffer that's going to store our data as we're collecting it. We have a state register, and then again, we have metastable and clean. So the data coming in gets clocked through multiple buffers, or through two. So one's metastable, one's clean. And then we say, and then assign ND good equals data good. That's basically just we have an internal register, and we're assigning that to the output of. We didn't have to do that. We could have made this a register output, but it was because I tweaked it from the test code. And then also we assign data out equals data buff. So we have these internal values and then the external outputs, and we're just assigning them to each other. It's going to be fine because I believe it's called a wire. Yeah. So, or I mean, these are set up as basically wires. So if we do the assignment statement, it shouldn't burn an extra flip-flop. It should use the same number of flip-flops. So always on the positive edge, the first thing we do is we do this buffering. We buffer the data coming in. And then based on our current state, so the first state is scene rise edge. So let's just go here. So basically, the first phase is scene rise edge. And this happens as soon as we see the bit go high. So as soon as we see the input go high, we enter phase scene rise edge. And then we wait for a prescribed period of time. So phase scene rise edge lasts a fixed period of time, which is the amount of time we wanted to wait until our data should either be a 1 or a 0. So once the data should be a 1 or a 0, we gather the data, and then we enter this phase data scene. So phase data scene, we wait in phase data scene until the edge falls again. Now for a 1, we're going to have to wait sort of, this half of this period of time that the 1 is high. But for a 0, if we have a 0 come in, we go from phase scene rise edge, we wait, we gather data right here, and then right as soon as we enter this phase data scene, immediately the input is already 0, so we're going to immediately jump to this phase scene fall edge. So for the 1 data, we're waiting around in this phase scene data for a while. For the 0 data, as soon as we enter phase scene data, we immediately on the next clock cycle enter phase scene falling edge. And so we had gathered the data in the middle here. Let's go back and look at that. So phase scene rise edge. So if we're in the phase where we've seen the rising edge, we assign a 1 to data good. That's just saying we're not, if we're in this state for sure, our data output is not valid, you shouldn't be reading it. So we're outputting a 1 to say the data is not good. So data good, remember, is active low. So a 1 means data is not ready for you to read. Clock count, just increment the clock count. If clock count's greater than clock pulses to data. So basically we're waiting in this state until we've waited the amount of time until we're ready to read the data. So once the clock's once we've reached the number of counts where we're ready to read the data, once that's the case, we assign. So basically we're doing a shift here. We have this buffer of 42 bits. We're shifting in data one at a time. So we're shifting the least significant 41 bits over 1. And then the last bit is going into this data clean. So the last bit is the data coming in, which is at the time we were supposed to read it. It's either a 1 or a 0. We add it in there. And then we add, so we got a bit. That means we read a bit. So we increase our bit count. And our current state goes to phase data scene. So phase data scene, once we're here, again, we're going to drop out of this phase very quickly if it was a 0. But while we're in here, still for sure our data is not ready to be read if we're in this state. The clock count gets incremented, and if the data clean is equal to if the data is equal to 0, that means we've seen the falling edge. Again, this is going to happen immediately if the bit's a 0. If the bit's a 1, we're going to have to wait here for a little while. So if the data is 0, that means we've seen the falling edge. We transition to a state seen falling edge. We reset the clock counter. So in phase scene fall edge, what are we doing here? So phase scene fall edge is we've seen the end of the previous bit. So there's a couple things that can happen. One thing that can happen is after we've seen the falling edge of the previous bit, we're done getting bits. If we've gotten 42 bits, we're done. The other option is that while we're in this state, we wait so long that it's a timeout condition. So one of those two things is going to happen. So phase scene fall edge. So the first thing is data's not good, so put a 1 to it. If bit count's 42, so this is if we've read 42 bits, we're done. And then in that case, we go to phase data complete. Otherwise, we start counting, right? So otherwise, we check if the clock count is greater than the clock pulses to timeout, we go into the timeout phase. So that's the two ways we can end our data collection is either we got all the data, all 42 bits, or we timed out. And both of those get handled here. And so, if we haven't gotten all the way up to clock, then again, still, I don't think I need to do this. I probably, oh yeah. So else data clean is equal to 1. Oh, sorry. If the data clean is equal to 1. Oh yeah. So this is saying, sorry. Yeah. This the other condition is. We see the data go high again. If the data goes high again before we time out, we're starting to see the next bit. So if we see the data go high again, we're starting to see the next bit. So we go to phase seen rising edge, and we reset the clock. Otherwise, we increment the clock. Yeah. So if we'd waited too long here, we time out. If we'd gotten 42 bits, we're done. If we hadn't gotten 42 bits and we haven't timed out, we start looking for the start of the next bit. That's what's going on here. Okay. So phase data complete. Here, this is where, so we say if data clean is equal to 1. So this is where, yeah. So basically this means if our data is complete, if we see a 1, that means we're starting. If we see a 1, that means we have a new set of data coming in. So in that case, we have to say the data is not good, and the bit count needs to go back to 0, and we need to go back to seeing the rising edge of bit number 0. Clock count gets reset to 0. Otherwise, data good is equal to 0. So when the data good is equal to 0, that tells the device we're connected to, okay, I dropped the data good low. That means the data is valid. You can read it. It's good to go. And so what's happening here is after the data is complete, after we've gotten all 42 bits, we're just going to pull the data good low to say that all that data is valid until we start getting more data. As soon as we see a rising edge, that means we have another set of 42 bits coming in. As soon as that happens, we have to say the data is not good anymore and reset the bit count and go back to phase seen rise edge and reset the clock count. And then phase timeout. While we're in phase timeout, we're basically just saying, 1, we're timed out, the data is not valid. We got a partial set of data. Our clock count, we can just keep our clock count at 0 and our bit count at 0, and then we're just watching for the signal to go high. So, and I probably should say if data clean, just for consistency, if data clean equals 1 B1, just so it's clear what we're doing. But this is just saying if data clean, if it, well. Change that. Okay, so again, we're timed out. Our data is not good. We're just waiting to see a rising edge. And as soon as we see a rising edge, we go back to phase seen rising edge. Otherwise, we stay in phase timeout. So we stay in phase timeout until we see another rising edge. Okay. Hopefully that makes sense. Okay. This is not great. Okay. All right, so what about generating the data? When we're generating the data, we have 3 phases. So basically, this is when we have 42 bits and we want to output it as a pulse width stream. This process of outputting is probably a little easier than inputting. We have 3 phases. Phase 1, where our pulse is always high. Phase 2, where our pulse is high if the bit is a 1 and low if the bit is a 0. And then phase 3, where we're just waiting based on the specs for the communication format, how much time you have to wait between bits. So this is fairly easy. As we're bit by bit until we've output all 42 bits. For every single bit, we go high for the full period of time of phase 1. In phase 2, we're only going high if the bit's a 1. We're going low if the bit's a 0. And then in phase 3, we're always low and we're just waiting to start the next bit. So for this one, PWM data out. Again, we have clock, load, 42 bits in, an output register D out. Phase 1, 2, 3, phase idle. What's phase idle going to be? That's when we're done writing data and we haven't gotten new data. So we're going to write all 42 bits, and then when we're done, we're just waiting until we see that load go low again, which means it's time for us to write more data. So, So, and then we have our parameters, which tell us how long we're waiting. So that's how long that's how long for phase one, how long for how long. Oh, sorry. So this is how long to go from. This is how long to stay in phase one. Yeah, how long to stay in phase one, how long to stay in phase two, meaning that we're going to count up to 20 clock cycles in phase one where we're outputting a 1, and then for the next 20 clock cycles, we're going to go low or high based on if it's 1 or a 0, and then we're going to wait until 50 to be done with the bit. And these are just fake too. I need to update these with the correct things. We have a 29-bit counter, a 42-bit data buffer. Our state is stored in 3 bits. We have a wire, which grabs the current bit. So we have a 42-bit buffer. We're going to shift that buffer and always be grabbing 1 bit position as our current bit. So once again, we're clocking the load in through this metastability thing. We want to see if the load falling edge. So again, we're doing the same thing we did with the LED. We're just saying, if the second clean one is high and the first clean one is low. So if the older data is high and the newer data is low, that's a falling edge. That's where we do something. Here's where we just shuffle that data through those registers. So on the positive edge of clock. So for every clock cycle, if we have a falling edge of load, that means it's time to go. So the data buffer, so we take all 42 bits and we store those into our data buffer, and we go to phase 1 of our current state. In phase 1, we're always outputting a 1. And we're increasing our clock until our clock gets to the pulses to the 0 edge, and then we go to phase 2. In phase 2, we are outputting current bit. So in phase 2, we're outputting the value of the current bit that we're grabbing out of our 42-bit string. We're shifting it, so we're just grabbing that most significant bit, and then we're shifting data through, so that most significant bit changes every cycle. If that bit's a 1, we're outputting a 1. If it's a 0, it's a 0. And we're increasing the clock count until we get to pulses to the 1 edge, and then we go to phase 3. In phase 3, we're always outputting a 0, increasing the clock count until we get to the clock pulses per period. And then, so after the bit is now, we're ready to start the new bit basically here. So after we've waited until the clock pulses per period, we're ready to start a new bit. But we don't start a new bit if we're done. So if our bit count's 41, this one went 0 to 41, the other one went 1 to 42. Either way says we've done all 42 bits. If bit count's equal to 41, that means we're done. We go to current state phase idle. So we've output all of our data. Otherwise, we go back to phase 1 to write the next bit. We shift that data buffer over by 1. And again, we're grabbing the most significant bit from the data buffer. So when we shift the data over by 1, that most significant bit is now going to be what was the bit 1 less significant than it. So by shifting the data, we're just sort of, and grabbing 1 bit position, we're just constantly, every time through this loop, we're 1 by 1 getting either a 1 or a 0 depending on the data that's there. And then we increase the bit count to say, hey, we're doing another bit, and we're resetting the clock. And then phase idle, all we're doing is outputting a 0. And so phase idle, we only enter, so phase idle we're just going to stay in until this happens. So this changes our, if load falling edge, we go back to phase 1. Otherwise, we would stay in idle here. So, okay. So hopefully that makes sense. Hopefully that's, hopefully that was helpful for you. I'm not quite sure it was. So once again, these output modules, the way I have it constructed in the code, are right here. So they're simulator data, which take in, so switch 15 is load, and then for the address, it's 9 bits of zeros, 3 bits of the switch data, and then you have the most significant bits of red, the most significant bits of green, most significant bits of blue, and then JB simulate instead of, JB simulate. For data out clock, JA simulate, and then the out data simulate and data good simulate. So The data good simulate is going to turn on LED 15. The data good simulate is just that load output. And then out data wire simulate, we're taking that and we're chopping it up and outputting it to the LEDs here. So again, LED 14 through 12, that's going to be the least significant bits of the address. So you should be able, if you feed in like an address 3, you should see the output be address 2 if it's working correctly. You should see, so if the input address is 011, what you should see show up on LEDs that are right above those switches should be 010. And then, of course, we have the most significant bits of each color showing up at the LED. Those should always be the same. So if whatever value you clocked in for color, as soon as you clock that in, you should see either that color show up on the LED, or you should see the address down by 1 and that color stay the same show up on the LEDs above the switches. So, all right, hopefully that helped. Thank you, everybody. Have a good weekend.